Hi, my name is Or. I'd like to give you a quick tour of our recent work where we introduced the notion of latent canonicalizers for improved sim-to-real transfer. Consider the following scenario. Given a large annotated data from a simulated source domain, like the digits shown in the figure, we wish to learn an efficient representation. By efficient, we mean that it can adapt to a target dataset using very limited labels. Note that while the simulated and real data are visually quite different, they share similar factors of variation such as font size, background color, and so forth. We wish to make our representation aware of this structure. A widely used approach is to disentangle the latent space to semantically meaningful subspaces. Most methods try to do this in an unsupervised manner. Recently, the effectiveness of these methods has been called into question. Instead, we opt for a fully supervised technique, which we now explain by example. Take this image of a digit. We assume a simulator that allows us to control important factors of variation such as font size, color, background color, etc. To leverage this strong supervision, we propose a variant of an autoencoder where, in addition to the standard bypass reconstruction, we introduce linear operators which we name canonicalizers. After canonicalization, the decoded image is expected to match the input in all aspects except assuming a canonical value in a particular factor of variation. This can be seen in the example where the digit font color in the input image has been turned into gray. The canonicalizers are learned through training with supervision on the image pixels. We train with both individual and pairs of canonicalizers to ensure composition. Finally, we add a classifier to ensure the digit class information is being captured by the encoder. Different from previous approaches, instead of structuring the representation directly, using the canonicalizers, we structure the way the representation can be manipulated. Our experiments demonstrate that when trained using our proposed method on simulated data, the network adapts to real data using only few labeled examples. In particular, note how our approach can achieve the same accuracy as a vanilla classifier does with 5 times less samples. We've repeated the same procedure, this time on a subset of ImageNet, where we have built a simple simulator by rendering synthetic 3D shapes on top of a random backgrounds, controlling object pose, scale, and background texture. Remarkably, albeit a significant appearance gap between our simulated data and the real one, our method outperformed baselines by a large margin. In summary, we've introduced the concept of latent canonicalization in latent space. Uniquely, we encourage disentanglement in latent space by constraining the way the representation is manipulated. We've seen impressive results on sim to real compared with baselines. For more details, please see the paper.